Good afternoon, and welcome to Preferred Utilities Technical Seminar on Carbon Reduction Emission Strategies for the Boiler Room. Carbon emission reduction is a high priority for a lot of universities and municipalities that operate central steam and hot water plants. This presentation will spell out the options that are available and show you how you can estimate the carbon savings from different boiler technologies. We're going to start with the regulatory environment for carbon emissions reduction. 9 Northeast states signed an agreement that caps CO2 emissions to 2014 levels and mandates annual reductions until the year 2020. Connecticut's Governor Daniel Malloy's Executive Order 59, signed in 2017, requires 45% carbon emissions reduction by 2030. Delaware has a plan that calls for 30% carbon reduction by 2030. Maine's governor released a plan to cut carbon emissions by 30% by the year 2030 as well. Maryland's General Assembly passed a bill that requires 25% reduction in greenhouse gas emissions by 2020. That's next year. Massachusetts passed a law in 2008 that requires 25% carbon emissions reduction by 2020 and 80% reduction by 2050. New Hampshire has a climate action plan that has a midterm goal of reducing carbon emissions by 20% by the year 2025. New York has an executive order with the goal of reducing greenhouse gas emissions by 40% by 2030 and 80% by the year 2050. New York has a long way to go. In 2018, New York generated just 4% of its electricity from renewable sources. Little Rhode Island passed 2 bills that require carbon emission reductions of 80% by 2050 with interim goals for the years 2025, 2035, and 2045. Vermont's bill requires 75% greenhouse gas emission reductions by the year 2050. Other states, including New Jersey, Wisconsin, Illinois, and California, have passed or are considering similar greenhouse gas emission reduction regulations. While these greenhouse gas reduction targets seem optimistic at the state level, they are attainable at the individual central plant level. Technologies exist today to reduce greenhouse gas emissions in modern boiler rooms by at least 80%. And we're going to show you how. We are going to start small and end big, beginning with fuel efficiency improvements in the boiler room. You can throw away your existing boilers and buy new boilers that will be a few percentage points more efficient than your current boilers. But fire tube boilers and especially water tube boilers can last decades if you treat them well. And it takes a lot of energy and other resources to manufacture a new boiler. So we're just going to say that replacing an entire boiler to gain a couple of efficiency points is outside the scope of this course. If you are going to buy a new boiler anyway, the new boiler will be a couple of points more efficient, most likely, than your old boiler. However, you can replace just the burners and achieve fuel efficiency improvements of 5 to 8%, depending on how inefficient the current burners are. New high-performance burners can lower excess air and increase burner turndown. New controls with oxygen trim can further lower excess air and decrease fuel consumption. If you burn less fuel, you emit less CO2. And these are technologies we've been doing for fuel savings for decades. You can indirectly decrease the carbon emissions from your boiler plant by reducing the electrical consumption of the plant by installing variable speed drives on your bigger motors. This includes the burner force draft fans, induced draft fans, and feedwater pumps. To convert from kilowatt hours saved to CO2, you can use the EPA's AVERT calculation. Nationally, the conversion is 7.07 times 10 to the negative fourth tons of CO2 per kilowatt hour. Regionally, that number can be different depending on the mix of generating equipment in each of the different parts of the country. If you're interested to find out what the conversion is in your area, you can Google the EPA AVERT site, find it, and pretty easily work out what the conversion is for your region. For instance, if you're in the Pacific Northwest where they use a lot of hydroelectric power, that number is going to be smaller than, say, Texas, where we get most of our electricity by burning coal. This chart has boiler or fan load on the x-axis and FD fan horsepower or kilowatt hours on the y-axis. The top line shows a typical fan horsepower curve without a VFD and damper control of the airflow. It's like driving with your foot on the gas and the brake at the same time, so horsepower reduction at lower loads is limited. With VFD control, we slow down the FD fan and run on the lower curve. The vertical distance between the two curves is your horsepower or kilowatt savings. This is the formula for fan horsepower versus speed out of the little Buffalo Fan Bible. Typically, burners are set up for about 20 horsepower fan speed at low fire. That gives them an electrical savings of 96.3% versus running at high fire with the fan running at 60 hertz. Preferred burners typically can be set up for a little lower VFD speed at low fire. They are typically set up for 12 to 15 hertz at low fire and will consume a little bit less electricity. To estimate the fuel and electrical efficiency gains possible with a burner and controls retrofit, you can use Preferred's online energy saver payback tool. You input the excess air, stack temperature, and load profile of your existing boiler, as well as the performance of the proposed new burner, and the web app estimates your fuel, electricity, and carbon savings. You can input your fuel, electricity, and retrofit costs, and the web app will output an ROI for the upgrade. The web app doesn't calculate the CO2 savings from the electricity reduction portion of the project yet. Our programmers are busy people working on other projects, but we'll get to it. In the meantime, you can use the EPA's AVERT calculation. Electrical savings from a VFD are more pronounced in boilers that run a lot at low fire. This makes sense. If you ran at high fire all the time, you wouldn't need a VFD. However, burner engineers are conditioned to always round up so they don't undersize a combustion air fan. As a result, most combustion air fans are oversized. If you look closely at the damper blades on existing burners, they may only be open to 45 degrees at high fire. This is very common. So when you retrofit one of these burners and add a VFD, you often find you only need 50 hertz or so to reach high fire. So this would be a case where even a burner and boiler that's run pretty hard could see significant electrical savings by adding a VFD to their forced draft fan. The same math applies to induced draft fans, but they are less common in modern boiler rooms. Many plants are putting VFDs on their feedwater pumps now too. The electrical savings you generate from that technology counts towards carbon reduction as well. Next topic. You can also fuel switch from a more carbon-intensive fuel to a less carbon-intensive fuel. This is part of the reason for the war on coal. These are the CO2 emission rates for the most common fossil fuels. This is based on the stoichiometry of burning different fuels. If you still remember your high school chemistry and balancing chemical equations, you can check these numbers. And as you can see, coal is by far the most carbon-intensive fuel, and natural gas is the least carbon-intensive fuel. You can take these numbers and make a handy little chart to estimate the change in carbon emissions changing from one fossil fuel to another. For example, if you switch from number 2 oil to natural gas, your carbon emissions reduction will be about 28%. All utility power plant boilers can be converted to natural gas firing. These boilers can have as many as 48 burners per boiler, but the good news is you can typically keep the existing fans, wind boxes, and burner registers. The existing burners can be fitted with gas injectors to burn natural gas. Getting the gas to all these burners on multiple firing decks requires a lot of valving and piping. But the good news is most of the existing boiler infrastructure can remain, and adding gas to a typical utility boiler is not a huge retrofit. Spreader stoker-fired boilers are more difficult to retrofit to gas. The process typically involves removing the traveling grate, sealing the furnace bottom with a new refractory floor, and adding wall-fired burners. The existing blowers may be reused and ducted to the new burners, or the new burners could have close-coupled fans attached directly to the burners. We've seen those retrofits go both ways. All central steam plant boilers can be converted to natural gas firing, including field-directed water tube boilers, packaged water tube boilers, and packaged fire tube boilers. To convert to gas in a central steam plant with packaged boilers, in most cases, the burners are going to have to be completely replaced. Gun-style burners for fire tube boilers and windbox burners for water tube boilers can all be replaced. Even Cleaver Brooks boilers, trademark, with burners integral to the front wall of the boiler can be replaced with preferred burner inserts. This video shows a crew replacing the burner in a trademarked Cleaver Brooks boiler with a new preferred burner. As you can see, with fast-working guys, this was done in 41 seconds. This was a fuel switching project at Bates College where they switched to a renewable fuel and achieved 82% carbon emissions reduction. But I'm skipping ahead. In actuality, I think that retrofit took an entire day. Burner retrofits are tricky to do right. You need a knowledgeable burner controls vendor and a representative from the plant to decide piece by piece which of the existing boiler plant components can stay and which need to be replaced to achieve the goals of the burner replacement. This includes the windbox burner fan assembly, the flame safeguard and fuel air ratio controls, existing instrumentation like pressure and flow transmitters, and motor starters or VFDs. Why spend money replacing perfectly good equipment if it will work with the new burner? The trick is, it takes pretty knowledgeable people to be able to look at your existing equipment and see which components can be reused and which should be replaced. And there should be a representative there from the plant as well. They might tell you that some of the old flow meters on a boiler have never worked well from the beginning, or just old and unreliable, and they want them replaced as part of a retrofit. That's why it's good to have someone from the plant there and a knowledgeable vendor. So recall, the pressure is on to reduce greenhouse gas emissions by 50 to 80%. So how much have we achieved so far? You can switch from number 2 oil to natural gas, and that's going to reduce your carbon emissions by 28%. If you install a high-performance burner, you can improve your efficiency on the order of 8%, depending on how inefficient your current burner is. You can add an FD fan VFD to your boiler and gain an additional 6% electricity reduction. Well, you lower your electricity consumption. That'll result in, on average, about a 6% carbon emissions reduction. And the total of all that is 42%. So nowhere near 50 or 80%. To achieve carbon emission reductions greater than 42%, you can switch fuels from a fossil fuel to a renewable fuel. And we've been doing this for decades. Probably everybody is familiar with landfill gas and digester gas. Both landfill gas and digester gas are renewable fuels made from renewable sources. We've been burning these fuels since at least the 1980s. The problem is they are gaseous fuels that can't be economically transported any distance. And even if you had the real estate to put in a lagoon or a digester in the middle of your campus, you're not going to want to do it because of the smell. And who has that kind of real estate close to their boiler room? If we didn't have a better solution, we wouldn't be doing this webinar. Preferred works with 2 companies that produce liquid biofuels that can be put on a rail car or on a truck and delivered directly to your facility. This unphotoshopped picture is proof. The first fuel we're going to talk about is RFO, or Renewable Fuel Oil. It's made by a company called Ensign. The feedstock comes from either tree trimmings or harvest residues from commercial tree plantations. The thinking is if this biomass wasn't made into RFO, it would be burned or left to decompose, and the CO2 would have hit the atmosphere soon anyway. So the CO2 that's made from burning RFO doesn't count towards global warming. RFO has been approved for all regulatory credits for renewable fuels, including RINs, LCFs, cap and trade allowance credits, and RECs. I can't explain what all those acronyms mean, but I can put you in touch with someone who can. This is a very simple diagram explaining where RFO comes from. The end products are liquid smoke that's used as a food additive, renewable feedstock sold to petroleum refineries, and RFO for steam and hot water plants. By the way, when you burn RFO in your boiler, it does produce a very nice wood smoke aroma. Because RFO is biogenic, greenhouse gas emissions from RFO are 88% lower than number 2 oil and 82% lower than natural gas. It's not 100% because it takes some fossil fuel to make renewable fuel and transport it to the job site. Preferred utilities can convert virtually any fire tube or water tube boiler to RFO. We're going to be supplying a stainless steel tank for the fuel, stainless steel lines, stainless steel pumps, and everything in the burner is going to be made of stainless steel. Preferred Utilities has converted fossil fuel fired boilers to RFO firing at Bates College, where we've done 2 of their boilers now, Youngstown Thermal, and the CNRC in Ontario, Canada, where we supplied a new Williams and Davis boiler burning Ensign's RFO fuel. Ensign typically amortizes the cost of the fuel conversion in a 5-year fuel contract. Even with the fuel switching costs, the price of RFO is close to the price of natural gas on a BTU basis. The video I showed you earlier was Bates College, which has converted 2 of their central steam plant boilers to RFO. As soon as our technicians finish tuning up their burners, Bates issues a press release touting their success reducing greenhouse gas emissions at their campus. These URLs are there, or you can Google the words Bates and renewable and you'll find these articles. They actually did an article for each of the boilers we retrofitted to RFO. Preferred is also working with a company called REG, the Renewable Energy Group. They're the nation's largest supplier of biodiesel. They make a fuel called biodiesel residual oil, or BRO for short. Think of BRO as the number 6 oil of biodiesel. Preferred started burning BRO in our 2 shop boilers in June last year. The burner on the left is a 1950s vintage Preferred rotary cup burner designed to fire number 6 oil. The burner on the right is our state-of-the-art low-emissions Ranger burner. They are both burning BRO. This is the startup data from one of the 2 boilers. Important things to note include BRO needs to be heated to 160 to 165 degrees F. If existing burners are using number 6 oil or number 4 oil, they will already have a pump and heater set that could be reused. Combustion efficiency is similar to that of number 2 oil. Stack oxygen indicates excess air levels of about 15 to 20%, which is typical of number 2 oil firing as well. Stack CO is less than 10 parts per million throughout the range. This is considered clean combustion for any fuel. Opacity was 0 throughout the boiler load. In fact, these burners were firing number 6 oil before we changed them out to BRO. It took no new equipment, not even a new oil tip, to burn the BRO. However, Dan Wallace, the preferred combustion engineer who tuned these boilers, did eventually change out the oil tips because he knew he could provide a little bit improved combustion with a new tip. And the data that I'm showing you there includes the new oil tip. So the key results of BRO firing. BRO had to be heated to an average of 162 degrees F. This is about the temperature we would normally heat number 4 oil or maybe low sulfur number 6 oil. CO emissions and capacity indicated clean combustion. Excess air levels were comparable to number 2 oil. Boiler efficiency was the same as number 2 oil. Preferred's 2 boilers have been firing BRO all during the 2018-2019 heating season with no downtime. Soon we will shut down these boilers for the summer, do a thorough inspection of the boiler internals as well as our oil tank, and then BRO will be available for sale to other boiler plants. The price of BRO is less than that of number 2 oil. Fuel switching costs will vary widely depending on the existing combustion equipment. A plant that already has the infrastructure to burn a heated fuel like number 6 or number 4 oil could require very little new equipment to burn BRO. A plant that's not set up to burn oil at all, of course, is going to need a lot more equipment. And Preferred's engineers can come out to your plant and do a detailed analysis of what you're going to need and provide you an estimate. So if we add up all of our possible greenhouse gas emission reduction technologies, including switching to one of the fuels we've shown you, you can get 82% by switching from number 2 oil to either RFO or BRO. You can get a little bit more performance out of a high performance burner. You can add an FD fan VFD and reduce carbon emissions by another 6% from the electrical side for a total of 90%. So you can reduce your greenhouse gas emissions in your boiler by up to 90% using commercially available technology. RFO is acidic, so the oil tanks, pumps, piping, and burner need to be made from stainless steel. Therefore, the ideal RFO candidate is a facility that has budgeted for new tanks, pumps, and burners and will burn enough RFO for a quick payback. BRO can be fired in most existing boilers or burners. The fuel has to be heated. BRO is more expensive than natural gas, but less expensive than number 2 oil. So the ideal BRO candidate is a facility that already has a pump and heater set, firing number 6 or number 4 oil. They can reduce their greenhouse gas emissions by up to 90% and spend less for fuel than number 2 oil. There are a lot of facilities in the Northeast that are still burning number 6 oil and are planning to switch to number 2 in the near future. These plants can switch to RFO or BRO and exceed all existing and proposed carbon emission reduction goals. So for next time, we'll do a deep dive into some of our fossil to renewable retrofit projects, and we'll tell you what to look for in a typical site survey when evaluating a renewable fuel boiler retrofit project. Stay tuned to David Bond's LinkedIn page for information on our next webinar. This slide shows my contact information. If you have any questions, feel free to contact me. I'll answer your questions or put you in touch with one of our full-time combustion engineers. The best way to get your questions answered is probably to email me, and we will respond right away. Thank you very much for your attention to our second technology webinar. I look forward to seeing you guys on the next one.